So we're going to move on and talk about estimating a population mean. And realistically, we're going to take the same ideas as estimating a population proportion and extend it. So we're going to have a different way to calculate the margin of error, and instead of being based on proportions, it's going to be based off of standard deviations. So we're ultimately going to see two things happen. It's going to depend, do we know the population standard deviation or do we not? Because we're going to need those things to be able to get a margin of error for that sample mean. So the sample mean, remember, is always denoted with X bar, and that is going to be our best estimate for a population mean, which is denoted with mu. So we're ultimately going to construct the confidence intervals the same way. The only thing that's going to change is finding that margin of error, E. We're going to have a slightly different formula for that. So I want to refresh just on all of the notations for everything. Mu, remember, is going to be our true population mean. So that's found by adding up every single data value and dividing it by the number of data values. It is the true mean. Again, this is very hard to calculate because if you're talking about heart rates for adults, you cannot feasibly ask every single adult. So this is where the samples come into play. So N is going to be our sample size, how many adults we actually ask. And then X bar is our sample mean. The way we find that is we add up all of the values in the sample and then divide by that sample size. So again, this is our estimate for the population mean. And we want to see within what interval do we get a particular confidence level. So we're going to need a standard deviation. And again, sigma is the true population standard deviation. But if you don't know the population mean, you're likely not going to know the population standard deviation. So this is where we're going to need a sample, and we're going to basically use all of those data values with the sample mean to find the sample standard deviation. And that's what we denoted with S. So it's found the same way as finding the standard deviation, except you divide by n minus 1 because it's a sample. And then E is the same thing we use for that margin of error. It's what we add or subtract to that sample mean to figure out a confidence interval. And the margin of error is going to depend on how confident you want to be. Now, ultimately, there are two requirements to be able to do this. You need to make sure that your sample is a simple random sample, and you need to make sure that either your population is normally distributed or the number in your sample is less or greater than 30. If the number in the sample isn't less than 30, there are ways to determine if the population is normally distributed given the sample. But just for now, for our time's sake and everything, you can assume that if the number is less than 30, then this other criteria is going to hold, okay? So as long as we have those two things, then we're going to be able to find the error, margin of error in one of two ways. It depends on whether we know the actual population standard deviation or if we don't. So we're going to start with the first case if sigma is actually known. Then what you're going to do is you're going to be really able to use those normal critical values from before. We find our z-scores, and then that gives us the critical value. So all of the same information from before is going to hold. In this case, your margin of error is again dependent upon the confidence level you want, and that is based off of those z-scores. So you have z alpha over 2. So if you want a 90% confidence level, then your alpha is 0.1. And remember, we could look at our z-table to see, okay, where at what value is 95% of the data going to be, because you want 90% of the data sitting between. So off to the side here would be 10% in total, which means you need 0.95 for that area to the left of here. So in that case, that critical value of Z ended up being 1.645. If you want a 95% confidence interval, then in this case your alpha is 0.05, and that value turned out to be 1.96, and 99% is the biggest. You need a critical value of 2.575. Then that margin of error was multiplied by something. What it ended up being for population proportion was an estimate for the standard deviation, which was found by multiplying the sample proportion times what I was calling the sample failure over n. But now in our case, this part up here, which you could distribute the square root to top and bottom, was an estimate for the standard deviation. So ultimately the formula is really similar. It still deals with the square root of n in the bottom, but in this case you actually know the standard deviation. Okay? So this gives you that margin of error that you want. So those critical Z values, you just use that Z table for, but again, you need to know that sigma is known in this case. So let's try an example with exactly this. Scores on an exam are normally distributed with a population standard deviation of 5.6. A random sample of 40 scores on the exam has a mean of 32. We're going to construct a 90% confidence interval estimate of the mean score. So remember, there are 2 requirements to be able to do this. Because the mean is always a bit more complicated. The first is that the sample is a simple random sample. And in this case, indeed, they tell us a random sample is drawn. So yes, that is a simple random sample. The second requirement is that the population is normally distributed. Or n is greater than 30. You need at least one of these to be true. But in this case, they tell us the scores are normally distributed, so this one holds. And also the number of samples is more than 30, so both really work. And in here, my value of sigma is known, so I can go ahead and use this formula for E. So in this case, my value of E is going to be my critical Z value multiplied by sigma divided by the square root of n. So this critical Z value, we already know because we want a 90% confidence interval. So that gives us a critical Z value of 1.645. Then our value of sigma is 5.6. And the number in our sample is going to be 40. The other thing I'm also going to need, in this case, they don't give me all the data values, so I don't have to find my sample mean, but they tell me a random sample of 40 scores on the exam has a mean of 32. So this is what I'm going to use to figure out what I need to add my error to. So in this case, I now know I'm going to have 32 plus something minus something. So that error is found by taking 1.645, multiplying it by sigma, which is 5.6, and then dividing by the square root of n, which is 40. So I'm going to trust you can plug these into your calculator. This should give you 1.4565. So now that I know that my error is 1.4565, I'm going to add and subtract that to my mean to get my confidence interval. So the 90% confidence interval is we take our mean and we add that error. We take our mean and subtract that error. So this tells us 32 is our mean. We're going to add the 1.4565, and then we're also going to subtract the same thing. So that gives us a lower bound of 30.5435 and an upper bound of 33.4565. And then for rounding purposes, let's round to 3 decimals. This gives us 30.544 and 33.457. So this gives us that 90% confidence interval. Okay. So with 90% confidence, I can say that the true mean is somewhere between these values. So the other way to write this is the true mean is smaller than 33.475 and greater than 30.544 with 90% confidence. If I wanted 95% confidence, then likely my error is going to be larger because I'll need a bigger range of values to guarantee I have that data within there. Okay. One other thing you'll often see, which I don't think I've shown you yet, but the other thing you can say is that your mean is less than the sample mean plus or minus that error. So this basically just kind of condenses this into one single inequality. So you can find your upper bound by taking that mean, which is 32, and adding the error of 1.4565. And then that lower bound is found by subtracting. So that's what we use the plus or minus for, okay? But like I said, realistically, it's very unlikely that we know the true population standard deviation because we are estimating our population mean. So in these cases, more often than not, sigma is actually unknown. If that's the case, I no longer get to use my z-scores to find my critical value. Instead, we're going to use something called t-distributions. It's very similar. It has a table that we're going to use to be able to find those critical values, but it's a slightly different distribution. So if our given population has a normal distribution, then when I find the value of t, which is found by taking the sample mean, subtracting the true mean, and dividing it by the kind of sample standard deviation, which is S over square root of n. This is a student t distribution. For all samples of size n, okay? So the margin of error for this is a little bit different, but it's actually gonna be more beneficial for us. So we're gonna see what the graph of this looks like, but really t-distributions are really important to us to be able to make inferences about our population mean. It's gonna have a bell-shaped curve. It's still symmetric like the normal distribution. The only difference is it's a little bit fatter in those tail ends. So if you remember, the normal distribution is really small at the ends, but our t-distribution is gonna be a little bit bigger. So this helps with the uncertainty when we're estimating these population parameters for limited data. So it's it's more forgiving basically. So the main difference is when you find the margin of error for a t-distribution is you're gonna look at a different table to find that critical value. So when we have a normal distribution, that margin of error is found using z-scores. But now if I don't know sigma, this is unknown. So I'm gonna use my sample standard deviation. And I'm gonna have a different value here that ends up actually being a little bit larger, again, because we end up with these fatter tails. So more data sits further out. So in this case, our margin of error with the t-distribution is gonna be a t critical value, the sample standard deviation, divided by the square root of n, okay? So we're gonna have t-tables to be able to figure everything out, but there's something important with this information, and this is the degrees of freedom. So the degree of freedom, which is denoted with a df, is the number of sample values that can vary after certain restrictions are imposed. So in our case, it depends on the amount of data that you have. That will indicate what your degrees of freedom is. So I want to consider an example for you. Say you have 10 test scores with a mean of 80. In this case then, what that meant is when you added those 10 test scores together and divided by 10, the result is 80 to give you that mean. So ultimately, if you were to solve for this sum, you would go ahead and multiply both sides by 10. That tells you when you sum up these 10 data values, it better equal 800, okay? So this tells me how many things I can freely assign. I can willy-nilly pick whatever I want for 9 test scores. So maybe the person on test 1 got a 0, test 2 got a 100, test 3 got a 12, test 4 got 19. Whatever it may be, I can freely assign those 9 test scores. But I need this sum to add up to 800. So once I pick my 9 test scores, the 10th test already is determined, so it will add up to 800. So 9 test scores can be assigned freely, but the 10th is determined. So that it will sum to 800. This means our degrees of freedom is 9, okay, because the 10th is determined. So in general, if you want to find the degrees of freedom, it's the number in your sample minus 1, okay? All right. So to give you an idea of what this t-distribution looks like, I got a nice little picture here for you, but you can see it follows a very similar shape to our standard normal distribution. So this curve right here at the bottom, which is that black line, is that standard normal distribution, which has a mean of 0 and a standard deviation of 1. And in this case, you can see those tail ends are super flat. When I have small data, my degrees of freedom is going to be smaller. So in this case here, my degrees of freedom is going to be 1, basically meaning I have 2 pieces of data. So you can see at the tail ends, you have larger amounts of data, but you still have a mean of 0 in the middle, and you still have symmetry to it. So the really nice properties about this t-distribution is it's still a symmetric bell shape. The other is that it still has a mean of 0. But it no longer is going to have a standard deviation of 1. It's actually going to be something a little bit greater. So this is no longer the standard deviation. And then the last thing to notice, you can kind of see these curves. So here is when the degrees of freedom is 1. When the degrees of freedom is 5, it's this curve here. And then when the degrees of freedom is 20 and 30, you can see it almost mimics that normal curve pretty closely. So ultimately, as n gets larger, so as your sample size gets bigger and bigger, the t-distribution gets closer to the normal distribution. And even our standard normal distribution. Okay. So ultimately here, that's why in the bottom of this t-distribution score, you don't just divide by the standard deviation, it's something that is a little bit bigger. And so it's still found in a very similar way, but gives you a larger standard deviation as a result. So the only thing we have to figure out then, because we'll be able to find the standard deviation of the sample, is what is this critical value? And so in that case, we're going to use t-tables to figure out what is t of alpha over 2. So I'm going to scroll to the actual t-tables first, and we will do an example with this. But again, this is not stuff you're expected to know off the top of your head. You're going to be given these tables. So often we're going to be looking at the area in 2 tails, because that's going to be the case where we have t of alpha over 2. So we have that symmetry on either side. So you can see the degrees of freedom is going to give us a different critical value for each degree. And then as we get closer and closer to n being large, you're going to see these values mimic the ones of our z values, our z-scores for critical numbers. So in the case, if you want the area in 2 tails, this would correspond to that 99% confidence interval. This would be 98%. This is 95%, 90%. And then finally, this last one is a 20% confidence interval. So say you have 10 pieces of data, that means your degrees of freedom is 9. And say you want a 99% confidence interval, this value would be your critical score here, because you would look at the 99%. If you have 20 pieces of data, your degrees of freedom then would be 19. And if you want a 95% confidence interval, your area in the 2 tails should be 0.05. So this would be that critical t-score that you would use. Okay. So let's try an example. A data set includes 115 temperatures of healthy adults having a mean of 97.9 degrees Fahrenheit and a standard deviation of 0.92 degrees Fahrenheit. We want to construct a 99% confidence interval to estimate the mean body temp of all humans. So here, my value of n is 115. That's definitely greater than 30, which is fantastic. And we know that body temperatures are normally distributed, so I'm able to use these process. But in this case, our actual sigma is unknown. Because this tells us 115 temperatures has a mean of this and a standard deviation of this. That is my sample standard deviation. So whatever those 115 temperatures were, they went and calculated the standard deviation is 0.92. So sigma is not known. This means we're going to use our t-distribution instead of z. Okay. So ultimately, I'm going to need a couple different things. I've got to figure out my margin of error, but I need a lot of other stuff to it. So I'm going to go through what each of these pieces is. Our sample mean is the 97.9 degrees Fahrenheit. That was the mean of the 115 body temperatures. Our sample standard deviation is the 0.92. The number in our sample is 115, which means our degrees of freedom is one less. So our degrees of freedom is 114. And then I'm looking for a 99% confidence interval, so my value for alpha is 0.01. Now the problem is I need to figure out what is my T of alpha over 2 when my degrees of freedom is 114. But if I go to my chart, you're gonna notice we have all of them up to 40, but then it starts jumping 5, and then it starts jumping by 10. Then once you hit 100, it goes to 200, and then 3, 4, 5, 6, or 5. Then it jumps up even further after that. And then you get to this value where it's large, and these are exactly the values that we were working with before with C. So there were the ones in our table earlier on in this video. So the problem is 114 degrees of freedom falls somewhere in between 100 and 200. So I don't have an exact row for 114. So in this case, you're going to use the row closest. And typically you would use the row down. So in this case, I'm going to use this row of 100 to figure out my critical T-score. Okay? Because I don't want to go overestimating in this case, because that would give me a not as confident of a value. You always do an underestimate for this part, because this will give me a bigger confidence interval. So in this case, here, there is no row. For 114 degrees of freedom. So use the row closest. Or again, typically the one that's under. So in this case, I'm going to use the information for 100 degrees of freedom. And because I'm dealing with a 99% confidence interval, my alpha is 0.01. The area in my two tails is 0.01. Okay. If I wanted just an upper bound with a 99% confidence interval, that's where I'll use the one tail, but we're not going to get complicated like that. So going back to my t-table, I want my area in two tails to be 1%. So I'm really just going to look at this first column. And I got to go to my degrees of freedom, which is right down here, which is 100. So my critical T value is 2.626. So way back up here, our T of alpha over 2 is 2.626. So now that I have all of this key piece of information, we can find the margin of error. So E is given by that critical T value times the sample standard deviation divided by the square root of the number in our sample. So T of alpha over 2 is 2.626. My sample standard deviation is 0.92. And then my value of N is 115. So again, gonna trust you can plug this into your calculator. This is about 0.2253. So from my sample mean, I'm going to add or subtract this to get that confidence interval I want. So the 99% confidence interval is our true population mean is less than our sample mean plus the error, and greater than the sample mean minus the error. So our true value of U is 97.9 plus 0.2253, and in between 97.9 minus 0.2253. So rounding, our 99% confidence interval for our true population mean is between 97.675 and 98.125. So this is our confidence interval. And again, another way you can also represent this, because this is what you'll see a lot of times in papers, is that your true population mean is less than the sample mean plus or minus that margin of error. So it'll be clear what you need to do when you're in an online homework platform. It'll give you an upper bound and lower bound, or it'll tell you to put it in this form. And then on any given written test, really doesn't matter which one you use. So the last thing we're gonna do is try to figure out what sample size do we need to make sure our population mean is within a certain margin of error that we want. So it's going to depend again upon whether we know our actual standard deviation or not. But for the simplicity of this, we're going to assume that we know the population standard deviation, or we're going to use a decent estimate for it. So we'll be able to just use our z-scores instead of figuring out a different approach. So to find the sample size required to find a population mean, we're just going to take that margin of error formula and we would solve it for n. So to refresh on just what that margin of error formula is for our normal distribution, the error is equal to the z-score times the standard deviation over the square root of n. So if you were to solve this, you again want to solve for n, so you'd bring this to the other side, divide by e, and then to get rid of the square root, you square everything. So really it just ends up with a bunch of stuff squared. So the sample size that you need is going to be whatever that critical z value is, times sigma divided by e, and then we go ahead and square it, okay? So let's try an example with this. We're told the pulse rates of 128 randomly selected adult males vary from a low of 34 beats per minute to a high of 122 beats per minute. We want to find the minimum sample size required to estimate the mean pulse rate of adult males. Assume we want a 95% confidence that the sample mean is within 3 beats per minute of the population mean. Like I said, we're going to do this two ways. We're going to find the sample size using something called the range rule of thumb to estimate sigma. So again, I don't know the actual standard deviation, but what I'm just going to assume for simplicity is that the standard deviation is about equal to the range divided by 4. So in this case, you have a high, you have a low, and so your standard deviation breaks this up into 4 equal pieces. So you take that distance and divide it by 4. And that gives you what sigma is. So if you want the number in your sample, it's equal to that critical z value times sigma over e, and then all of that squared. To get a 95% confidence interval, this means our z critical value is going to be 1.96. So just going back to our table. Our value of e in this case is 3 beats per minute. That's our error. And the way we're estimating sigma is we're taking the range and dividing it by 4. The range is again just the low value or high value minus the low value. Highest value is 122. Lowest value is 34, and then we divide it by 4. So that gives us 88 over 4, or our standard deviation is going to be 22 beats per minute. So the sample size we would need would be 1.96 times 22 divided by 3, and then squared. So plugging in that into your calculator, you should see it's about 206.59, and you can't have a fraction of a person, so we always round up for that sample size. If I round down, I can't guarantee it's 95% confidence interval. So in this case, using that estimate, I should take a sample of 207 people to guarantee that I have a 95% confidence interval with an error of 3. Now, if I assume I find the actual sample standard deviation, and that's 13.7, if I assume that's the true standard deviation, let's figure out how many people we need here. So nothing else changes except the value that I'm using for sigma. So the only thing that changes is our value of sigma is now 13.7 instead of 22. So this was found just using the sample standard deviation. So our value of n is still the same thing, but now times 13.7 in the top. But all of the other information is the same. So if you plug this into your calculator, you see this is about 80.11. Again, can't have a fraction of a person. So to guarantee I have the correct confidence, I need to round up. So if I have that sample standard deviation, then I'm going to assume that I need 81 people to get a 95% confidence within 3 beats per minute of the true population mean.